Welcome back, guys. Moving on to another test question. So the doubling time for a certain type of bacteria is 2 hours. We have to sketch the graph of the function for an initial population of 5. How would the graph and equation change if the doubling time was 4 hours? So let's first start off making an equation for this information that we're given. So as we've been doing this whole chapter, right? This is exponential growth. Now, this general format, if you remember from the lecture videos, I mentioned it's more so for cases where you have like per year, per minute, per hour, per 1 hour, per 1 minute, per 1 year. Notice here that we're told the doubling time is 2 hours. And whenever you have something like it's doubling every 2 hours, tripling every 3 hours, or maybe it has a half-life of 5 hours, this exponent is going to have a denominator. It always has a denominator, but when you have like a per minute, per hour, per year type of question, then that denominator is always 1. So we could just put a t there. But in this case, we have a doubling time of 2 hours. So we know that the exponent is going to have a denominator. So let's say the population of this bacteria as a function of t, let's say t is what? The number of hours? So it's going to be the initial amount. The initial amount we're told is 5. And then it's doubling, right? It's a doubling time that we're given. So we know that this base is going to be 2. And it's going to be t over 2, which is that doubling time there of 2 hours, right? If the doubling time was 3 hours, this would be t over 3. And this is 2 because it's a doubling time. If it was a tripling time, then this base would be 3. And the r that we plugged in here was 100%. When something doubles, it means that it's growing by 100%, right? So 100% in decimals is 1. 1 plus 1 gives us 2, right? So that's how 1 plus r and 2 relate. I mentioned that in the lecture videos as well. So this here is our equation. So they want us to graph this equation. So what I'm going to do is I'm actually going to use values for t that go up by 2 because the doubling time is every 2 hours. So I'm going to start with 0. Let's do 2, 4, 6. Let's just go up to 8. Right? So if I plug in 0 here, 0 over 2 is 0. 2 to the power of 0 is 1 times 5 just gives us 5, which makes sense because 5 is the initial population. Now, if we plug in 2 here for t, 2 over 2 is 1. 2 to the power of 1 is 2 times 5 is 10. Notice that it doubled, and that makes sense because the doubling time is every 2 hours. So every 2 hours it's going to double. So we know if we plug in 4 here, we should get 20, right? It's doubling from that 10. And you can show that by plugging in a t-value of 4. 4 over 2 is 2. 2 to the power of 2 is 4. Times 5 is 20. So then doubling again every 2 hours. So this would be 40. And then doubling this 40, this here is going to be 80. So now I'm going to take these points here and then plot them on the graph. So 0 and 5, that would be here. 2 and 10, right there. 4 and 20, that's going to be like right here. 6 and 40, up here. Let's make this a little bit more, yeah. And then 8 and 80, 8 and 80, that's going to be like right up here. Right, so basically, it's looking like that, right? So exponentially growing, right? You could have also used the transformations to do this. So we could have, the base function is 2 to the power of x, and then you could have picked positive x values. So maybe, yeah, you could do like 0, 1, 2, 3, all the way to 10, and then maybe transform those, but usually with word problems I just like to make a straight table of values. Usually you're dealing with time, so you know everything's just going to be positive. Okay, so that is the graph for this table. And they also asked what would happen if the doubling time was 4 hours. How would the equation change and how would the graph change? Well, notice with a doubling time of 2 hours, we could change this exponent to look like 1 over 2t, like that. So notice in this case, the k value, 1 over 2. And what does that mean? That means that there's a horizontal stretch by 2, right? So you're taking this graph, you're horizontally stretching it by 2. Remember, you always flip the k value when you start describing the transformation. So if the doubling time was 4 hours, then it wouldn't be t over 2, it would be t over 4, and this would be like 1 over 4t. So that means the k value would be 1 over 4, and that means there would be a horizontal stretch by 4 instead of 2. That's what the difference would be. And that would be the difference in the equation. Just that part would change. That denominator would be 4 now. How would the graph change? Well, it's going to be horizontally stretched more, right? The factor's bigger now. Before it was by a factor of 2, now it's by a factor of 4. So what's going to happen is this graph, it's not going to exactly look like this, but it's going to look more like that. It's going to be horizontally stretched more, right, by a bigger factor, right? So it's not going to increase as quickly. And that makes sense because if the doubling time is 4 hours instead of 2 hours, that means it's taking longer to double, right? If the doubling time is 2 hours, it's increasing faster. It's doubling quicker. But if the doubling time is 4 hours, it's a little bit stretched out, right? So you get that larger horizontal stretch, so it's not going to increase as fast. So the graph would look something like this. It would be a little bit more stretched out to the right, right? So that's how the equation would change. That's how the graph would change if the doubling time was 4 hours.